Welcome back. This is the fourth part of this introductory series on neurotics. Today we will take a deeper look at node properties such as shapes and population sizes. By the end of this video you will understand every parameter they have. We will also cover how flow fields work, which are essentially a way to morph your populations into a vast variety of shapes. This way you will have full control over your network. We have a lot to cover in this video, so let's jump right in and start with the first type of node, the neuron ring. First, let's talk about how this ring is connected, because this is the most important part in understanding what it is doing. The neurons are placed on a circle with equal distance. Their positions are then evaluated with a special function which returns their direction in an artificial rotating field. These directions are then used to calculate how excitatory or inhibitory and how strong their connections to the other members of the ring should be. This is done by using a simple cosine similarity which returns a number between -1 and 1. This is done for every neuron in this node, and by the end we get a structure that excites its neighbors while silencing the neurons on the opposite half of the ring. This way we ensure that the signal doesn't spread out to the whole ring, and we can trap signals in the structure. To create a ring, we create a node. And since it's a special structure, we don't add a population like we did the last time. Instead, we select a different node type by opening the dropdown. Here you can see the different types of nodes we can select from. The node properties are often similar from type to type, but there are individual differences, mostly at the bottom of this menu. We already talked about center and displacement, but you can also rotate the structures by altering the initial degrees. This rotation happens around the center of mass and thus is global relative to the z-axis. We can also scale the structure in any direction we want, which ultimately will alter the behavior of the firing patterns. Like before, we have access to every neuron type Nest offers, but for simplicity we'll stay with the defaults. Here you can set the amount of neurons and the radius of the ring. At the bottom you see the weight, which is multiplied by the value of the cosine similarities for each neuron, which we already have calculated. You may be tempted to write negative value for the inhibition, but please don't. This already has a minus sign internally, so that everything happens like it should. Think of these values as signal strength. I admit this structure has the potential to become a particle accelerator if the weights are set too high, so keep that please in mind. The weights should be chosen wisely. There is actually not much more to say. The name comes from the initial attempt to create a basic signal attractor as a bigger building block, which allowed for the signal to travel in the counterclockwise direction because no excitatory connections had been made in the other direction, only inhibitory. But later it became clear that to encode information you need uni and bidirectional signal paths. That's why there is a small checkbox for bidirectional rings. There are more or less similar structures available, the rods and cones, similar in the way that their connections to their neighbors are excitatory while being inhibitory to the opposite half of the cone. There are two quirks to them. First, the connections are chosen randomly, so it's not an all-to-all connection. Second, the height dimension dictates signal direction, which makes the rod or cone a temporal transformation of the signal, along with the usual side effects, the trajectory of a signal through neural tissue experiences. It's by no means a signal attractor, that's what I'm trying to say, and a weak signal dies here much faster than in the ring. The initial parameters are the same as for the cubes and rings, so explaining them would be redundant. The shape-specific parameters here consist of the number of neurons, height, upper radius and lower radius, and that's all. By changing these, you automatically change the shape. I initially used them as spatial signal collectors, where I inserted them into bigger populations and spatially connected them to the nearest neurons of said populations. But they became a basic building block during this project, and you will soon see why. Now we'll come to the third type of node, the blob. It's just a uniformly distributed set of neurons around its own center of mass, with a maximum distance to that point. They are initially sparsely and excitatory connected, with a low probability for connection. But this does not make them uninteresting, because they introduce selective computation and signal path trajectories which may vary in time and strength. The only shape-specific parameters you have here are radius and the number of neurons. That's all. The fourth type of node is the grid. Even though this is probably nothing that would occur in nature, it's a great test subject for connection rules. I usually use them to check if my proposed topology works out before I start connecting bigger networks. Here you can check if your signal goes through. As a nice side effect, it resembles the usual visualization style of artificial neural networks and thus can be used for explanations. But it can also be used for controlled convolutions, especially when using topological connection rules which don't care about position. The only shape-specific parameter is the side length of the grid, which is counted in neurons. As the, for now, last type of node, we have the cube. Consider it as your patch of neural tissue that you glue together. These are the ones that fill the space. These are the shapeshifters. They initially start as evenly spaced neurons, and with the help of some questionable underlying algorithms, they provide locally interesting neighbor relations based on the neural distribution of your choosing. But you can also turn that off and also use just random positioning based on your distribution. The parameters for the grid size are separated by axes. Each axis has its own directional density. We can have everything from one neuron to really hard to estimate numbers, it's up to you. The specific algorithm I mentioned takes a ton of time to compute and is only partially suitable for bigger patches. Don't use it if you have only one neuron type per node. Please trust the developer here. This just does not make any sense and is a huge waste of your time. It can be turned off if you uncheck the first checkbox right above the grid size. The sparsity value influences how much the algorithm favors initially grouping similar neurons together, leading to emergent structural patterns and some subtle benefits in coordination with the flow fields, which we will come to shortly. If you uncheck the box, then this value loses its meaning. I recommend having the sparsity factor around 0.9. This is the final part of this video. We've reached the point where we are ready to talk about one of the most important editor features Neurotic offers, flow fields. The idea behind flow fields is to use a bunch of simple equations to morph the neural structure based on the forced neural experience. Or more precisely, we take the positions the neurons had when the cube was initialized, and each step we move them in the direction of their respective vector in the field. I admit this sounds abstract, but what you actually do is say, hey, I placed this cube here, but I'd like to have a slight curve, or I want a tail, or twist this into a spiral, or whatever you like. The reason I think this is a good alternative to precise modeling, I mean placing each neuron exactly where it belongs, which by the way you can also do here, is that biological systems often follow a set of rules, especially during brain development. You have chemical gradients guiding axon growth, mechanical tension shaping tissue, and genetic programs unfolding over time. None of this is place neuron A at coordinate X. It's more like follow this gradient, respond to this signal, and grow in this direction. Flow fields capture that logic. Instead of micromanaging every position, you define the forces and let the structure emerge. This way, the resulting network reflects the process, not just the outcome. The goal is to make experiments that mimic biological systems physiologically plausible by approximating the structure instead of reconstructing it. This serves as a reasonable trade-off between biological accuracy and practical usability. Implementing flow fields is straightforward. Each population has exactly 3 equations, each of which describes the drag in the x, in the y or in the z direction. You choose the coefficients and the power a coordinate should have, and you add some additional extra terms, and you are done. Initially, these equations are chosen randomly with some soft clipping so that you don't fly straight into the sun, but since the distortion through the flow field is initially deactivated by setting the parameter dt to 0, thus eliminating any influence the flow field could have on Neuron positions, it doesn't matter. You can control the influence of the flow field by changing dt and the number of steps, but since no mortal being is able to visualize 3D vector fields in their head, Neurotics offers a visualizer for these fields where you can watch the network evolve in shape as many steps into the future as you like. This feature is available only for cubes, since they are the only ones that are affected by these fields. Each other node type has only the basic transformation rules, but since they are functional substructures, that's fine. Anyway, here you can see what happens if you take the current position of the neurons and apply the force field a few times to their position with a certain dt. This way you can morph your structures as you like, and let me assure you, most of the time you can slightly nudge an equation to get exactly the shapes you want. A bigger dt means more influence by the flow field, but less precise movement along the trajectory. More steps and a smaller dt is always a good option, and since it's internally built on NumPy, you shouldn't worry about too many steps. Better watch your equations. I generally don't recommend creating functions with a bigger power than 3. I know of no biological system that works under forces of this magnitude. Trying things out in the flow field visualizer doesn't change your nodes. You can see it more like a tool that predicts what happens next if you choose a certain direction. Here you can play around with different equations and choose the one that fits your needs. This tool aims to give you the freedom you need and to minimize your efforts by procedurally create the structures you want and allowing you to quickly check if your idea works. In combination with the live interaction tool, Neurotics becomes a neurological lab on your desktop computer. It's crazy to say that, but it's technically true. Anyway, this video is pretty long, so I'll make a cut here. Thanks for sticking around. I hope to see you in the next video and have a nice day. See ya.